Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Cadence with Frank Ferro. We're going to talk today about LPDDR6. Frank, the whole industry is buzzing over HBM4, but it's not the only game in town, right?
That's correct. For the AI market, designers are looking for flexibility now in their memory systems. Sometimes you need raw bandwidth, but raw bandwidth isn't the only thing as these AI um, networks mature. And recently, their JEDEC announced LPDDR6, which is the latest in the mobile memory. Now, we think of LPDDR6 as something that's going to go in your cell phone or in a tablet or in a PC, but it's moved beyond that. And one of the reasons it's moving beyond the mobile market is because LPDDR gives you a really good balance of performance, of power, and also capacity, which is becoming very important. The other advantage of LP6, it uses more traditional packaging technology, so you don't have to go into these 2D systems.
Let's take a closer look.
Okay.
Frank, what are we looking at?
Okay, so this is an SoC that I have a bunch of these little square boxes are the physical layer or the PHY and the memory controller. And as we started talking about with LPDDR, one of the advantages I mentioned of LPDDR is it has good speed and good capacity, but the speed still is for a lot of these AI systems, you're going to need many DRAMs, and that translates into many more PHYs on the SoC. So we've actually, if I go back a generation, LPDDR5X, we've had customers who are building these systems now for AI, and they're putting as many LPDDRs as they can get on a wafer size chip. And so what that means is by putting many on, I get lots of bandwidth, I get lots of capacity, but I have to deal with now a lot of pins as well.
A lot of this is cost-based, right? Because you think about where HBM4 is going, these are generally $100 million designs.
Right. Yeah, so cost is a big factor. So one of the advantages of going with LPDDR is now you're back to your traditional SoC in a package on a PCB. So that immediately saves you a lot of cost from a manufacturing standpoint. You don't have to go through the 2.5D type of manufacturing. So that's a big advantage. But on the other hand, then now you've got to put a lot more chips on there, a lot more DRAM on there in order to get the same kind of bandwidth you need for some of these AI, whether it's low-end training or AI inference. And just inference is once these models are trained, now they get pushed out into the end devices, whether it's a car or whether it's a camera, a security camera, even a cell phone. So those models get pushed out into these devices that are much more cost sensitive. Even at the edge of the network, they push these models. So you've got to now look at, you just don't need the raw bandwidth. Now you're going to have to look at a cost. And as the models are growing in complexity, you also need more capacity.
This is the same problem that you dealt with when you dealt with GDDR, right? What's the difference on LPDDR versus GDDR?
So GDDR is absolutely a very good memory for AI inference. GDDR has a bandwidth all the way up to GDDR7 announced is up to 36 gig. So at 36 gig, you get lots of bandwidth, but you still need that capacity. So I think what LPDDR, if capacity is a big requirement, you can look at LPDDR6. If you just need raw bandwidth, GDDR is a great solution. So now these system designers have a lot of flexibility. So raw bandwidth, high bandwidth memory. For capacity balance, you can use LP. If you need just bandwidth, you can go with GDDR for AI inference.
What's changed in LPDDR6 versus 5?
Okay, so one of the big differences is the performance. So the JEDEC spec now goes up to 14 gig. The previous generation was 9.6, and there is a variant that goes to 10.7. So you're getting more bandwidth, but they're also increased the number of bits. LPDDR5X was 32-bit channels, two 16-bit channels for 32 bits. Now we've got a total of 48 bits with two 24-bit channels. So just the additional bits gives you more data, and also you could use those for reliability as well. And then, so that gives us 691 gigabits per second, which is more than 2x of the previous generation.
And the whole problem here has been that you can't scale SRAM, right? So now you need to start looking outside of where do we put this data? How do we access
That's
it?
right. That's right. And how do we access it and as cheaply as possible? That's right. And power is still, a big concern in the data center. So having LPDDR gives you a good balance of power. So one of the changes that have been made, like I said, the channel, the 12-bit subchannels, now we talked about with HBM how you need more resolution. So same thing here, right? The designers can have more flexibility in how to customize data to match up with the word sizes in the DRAM.
And this data is much more valuable than it was in the past too. So what's changed on the security side?
Yeah, again, when you were thinking about your mobile phone or thinking about a laptop, reliability and security are certainly important. But now in a data center, these are running all the time, right? These do not shut down. So you have to have the ability to really look on errors. So they've added a whole, I just put a sample of some of the changes from a reliability and security standpoint. They have per row activations, link protection, on-die ECC, MBIST, and I've only, like I said, there's a list, much more. So the thought from the JEDEC committee is let's make these really specific to the data center, not just mobile.
And how about power versus some of the other types of DDR?
I mean, this is still going to be your go-to memory for mobile. So the power improvements have changed, and you have dynamic frequency scaling that continues to improve. You have lower voltage, lower operating voltage as well, and so those power improvements are there as well. So again, it's going to be targeted for mobile, but now with the added features that it can work in the data center.
Is there a capability to mix and match?
Absolutely. What Cadence announced recently was our LP6 5X Combo PHY. As the technologies, with all the DRAM technologies, you transition from one generation to the next, and there's always a little bit of confusion and risk in terms of when those DRAMs are available. So the PHY that we announced supports both LP6 at 14.4 gig and LP5X at 10.7 gig. So you have the flexibility to say, if I want to go with a design that's LP5X and then later migrate to LP6, you can do that with the single physical PHY and controller.
And that physical layer is really just to move data very quickly back and forth between processors and memory, right?
Yes, it's the interface. Yeah, it's the interface on the SoC between the DRAM. That's right. That's correct. And so that's where we get into the whole topic of now, back to this picture again. We really go back to signal integrity, right? So now I've got lots of pins. I've got to move these the DRAMs are sitting out here. I didn't draw the DRAMs, but now you've got a move to move, 48 bits of data times however many physical layers you have on the SoC. And you, with LP now, you've got longer distances to go. And so how do you design the bump outs on your package? How do you route all those signals? And how do you do that with minimizing crosstalk, insertion loss, things like that? So again, Cadence provides both the tools and the know-how how to build these large complex systems in terms of getting very good signal integrity and very, very good wide eye openings.
Frank Ferro, thanks for a great explanation.
Thanks.